All right. So the question is that show that all the square of any integer is in the form of 4k or 8k plus 1, right? So the statement to prove that, we want to show that, what do we have to prove? That the square of any integer can either be can be represented in the form of 4k or 8k plus 1, right? Where where k is where k is an integer. Suppose we are taking it in this way, right? In simply terms, we are like trying to show that when you square any whole number, let it be positive, negative, or 0, the result will always be either a multiple of 4 or 1 more than the multiple of 8. Um, and it will never be it will never be something like 8k plus 2 or 8k plus 3, etc., etc. Okay, not be. Always be. Okay, so this is the thing that we're trying to prove over here. So the main strategy we're trying to follow is a division algorithm. So like what does division algorithm actually say? Informally, it says that when you divide any integer by integer b by any other positive integer a, all right, so you will get a unique quotient. We will always get a unique quotient q and a unique remainder r, uh, such that b equals to aq plus r. So we all know that where r is a remainder, r remainder, and r will always be between 0, r, and a, right? So yeah, my bad. So this is what r will be, and q is the quotient, where q is the quotient. Q is the quotient. Done. Now we all know that the remainder cannot be less than 0. Okay, and it cannot be more than a or equals to a, because if it was more than a, then it would have added that extra 1 to the quotient, and the remainder would have been r minus a, right? So suppose that hasn't happened over here, and suppose we are taking that. So, and for this problem, for this problem, we are considering to solve this problem, we will consider a equals to 2. So this is very important over here, right? So after making this assumption, first of all, what we will do that if we divide any integer by 2, we will either get we will get two cases. So okay, suppose let it be any integer. Let's suppose b is an imaginary, not imaginary, yeah, let it be an imaginary integer, correct? So after that, what will happen? If we divide b by 2, either we would get some quotient q, or we will get some quotient and a remainder 1, right? So this is what we would get. So for this we can write b equals to 2q, and for this one we can write b equals to 2q plus 1, right? Where b is even and over here b is odd. So after going from here, suppose we take b equals to 2q. So we will do this, yeah, side by side. Alright. Suppose that b equals to 2q. Then what will happen? For b equals to 2q, if we square both the sides, b square equals to 4q square, right? So we all know that q is an integer. Q is an integer. Q is an integer. And then q square would also be an integer. Correct. So from here we can say that b square equals to 4k, where supposedly k equals to q square. I'm just representing q square as k. Alright. Now if we take this, for the case of b to be odd, or suppose the integer is odd, then if we square that, b equals to 2q plus 1. Now after squaring, b squared would be equals to 2q plus 1 whole square. Supposedly everybody watching that video knows the expansion, so it would come out something to be 4q square plus 4q plus 1, right? Now if we look over here, we can take 4q as common, so it would be q plus 1 plus 1. Alright, so that's q square plus q. So the thing is that over here we have to make another observation. It's that q into q plus 1 always even. Why is that? If q is even, then so we get it that it's even. If q is odd, then q plus 1 is even. Correct. So after getting this idea out of the way, we can say that q is even. So as q is even, and supposedly we take q, so as it's always even, so we can say q into q plus 1 to m. We can say that, right? Because the whole thing is even, so it's some integer multiplied by 2. Correct. So after saying this, if we insert in this equation, if we insert this value over here, so we can say that four into 2m b square equals to 4 into 2m plus 1, right? So it's 8m plus 1, right? So we can also say it's 8k plus 1, because k, supposedly we are taking m equals to k, right? So from here we have also proved for even, done, right? So Hence proved. When b is even, b square equals to 4k. When b is odd, b square equals to 8k plus 1. Right, done? Alright, so after this, there might be an idea. So over here, what I was trying to say is that when b equals to 2q, or even, correct, when b equals to 2q plus 1. And now, let's see some examples. After doing all of this, let's get some examples and like concrete, let's get a concrete view about this idea. Right. So let's take for b equals to 4 maybe. Alright. So what's 4 square? 16. Can we represent 16 in the form of 4k? Yeah. 16 can also be written as 4 into 4. Right. Yeah. Now let's take for b equals to 5. So what would be b square? 25. We can also represent this. See. So it can be represented in the pattern of 4k. And for this one, we can also represent this as 24 plus 1. And what's 24? 8 into 3 plus 1. 8 into 3 plus 1, right? So it's represented as 8k plus 1. Fantastic. Now, you guys might be worried about what if the integer is a negative number. It doesn't matter because after square, everything turns out to be positive. So it shall be 9. And we can represent this as 8 into 1 plus 1. So it is also similar to as 8k plus 1. Right. So it also fits the case. So from here, get an overview that every number can be represented, every square, so the square of every integer can be represented in the form of 4k, or in the case of it being odd, the integer being odd, the square can be represented in the form of 8k plus 1. Correct? Thank you.